last year. So our speaker, Kirill, is going to be talking about JavaScript a la carte, I believe, right? Mm-hmm. Yeah. Oh.
Hello, my name is Kirill. I'm going to talk about extensible formalization of JavaScript. I'm doing my PhD at the University of Turku, and my supervisor are Mikhail, Barash, and Jaakko, Järvi. So the first question is why JavaScript? And the answer is that, as we heard before, it has quite well maintained standard and transparent feature adoption through the T39 committee. It has a lot of dialects that should help to evaluate how extensible modular formalization is, and it's an industrially used language, so it's interesting how the mechanization will be shaped around that one. There are a lot of existing mechanizations of JavaScript, but they are all old and they are abundant, and one of the reasons why it is the case, it's that mechanization in general are not modular, and it's hard to extend them, maintain them, and keep up with evolving language, especially with JavaScript, which evolves fast. So I will tell how we plan to make proof about the language extensible, what we've done so far, and what is yet to be done. And I will start by investigating why it's hard to extend mechanizations. And if we try to extend the behavior around the type of our very small expression language, we find out that it's okay. But if we try to extend a representation of our language, it will fail, because we need to handle all the new cases that appear, and it doesn't scale with the amount of proofs you do. That's an instance of a very well-known problem called expression problem. And there is a certain solution to it called data types a la carte. In boxes, there would be a la carte representation of things that are not in the boxes. And the first thing is, how do you encode the type in order to fight the non-accessibility with adding new cases? And the answer is that you split the recursion and the description of the type itself. What is the fixed point that doing the recursion? We will discuss that a bit later. Let's focus now on how the extension looks like. We add multiplication. We add another functor that, and you can see that x in our functor corresponds to the recursive mention of our type that is handled by the magical fixed point on our functor. And here, all we need to do in order to extend our type is add it to list of functors that are fixed point on by a fix. So let's see how we can write functions on it and then lemmas. So this is the simplest possible function you can write in this small language that just evaluates expressions to natural numbers. And at first, we will need to write a functor-wide definitions for each functor we fixed point on. And that's quite simple and corresponds how you will write it on the usual inductive type. But the caveat is that here we don't mention the type that we are going to recurse on, and recursive call is provided explicitly in open recursion style, because we don't know anything about overarching language. Let's shorten it up and see how we then compose them. So it's a fixed point, and so far the only thing we achieved is to move the payload of our proofs into functor-wise definitions, but things will break as we extend it. So let's return to fixed point operator and see what it actually does and how it's described in data types record. It's described as a data type that finds the fixed point of our functor, but unfortunately it allows us immediately to derive falsehood, so it's unapplicable in theorem provers. So let's investigate a bit further what it's actually doing. And by looking at the types it generates, we can see that for each particular type, we can write the definition by hand. And that was noted by RocqPL'26 paper that is one of the later paper that explores this approach. So then let's do fix as a metaprogram to extract it outside of our language and permit to use it without enabling to deriving falsehood. Composition can also be extracted from language then and made into a metaprogram. But as so far, we still need to manually add our cases. And the trick is, that was also one of the contributions of RocqPL'26 paper, that with knowing on which type we're doing our induction, we can actually find the functor-wise proofs in our environment. And that will solve our problem and make types extendable by hand, but proofs and theorems extendable automatically. There are more approaches that solve this problem, but all of them suffer from the same downside, is that they are indirect. And if one looks through the papers that try to mechanize existing languages and acknowledge existence of modular approaches, the single most cited reason for not using them is that they introduce indirectness. And RocqPL'26 approach is the most direct approach out of them, because first one is using the approach built in on interaction trees. Another one, program logic Carte, I think, uses containers to encode the language, to encode the class of functors you allow to fix point on. And extensible meta theory through family polymorphism extends the compiler itself to incorporate their way of extending types. So goals of this work, which is very much work in progress, is to start with Lambda JavaScript, which is existing from mechanization of JavaScript, extend with core control flow, object mutability, and exceptions to see how well behaved the a la carte approach is. And then extend it with reactivity, because that's one of the proposals in T39 pipeline. Probably implement React dialect to compare them, while maintaining the theorem of progress that you can do step if you're not a value. That local closeness is preserved because we don't have types in JavaScript. The reduction uniqueness to disallow rules that just assign error to everything. And then automate it. We use LP to automate our metaprograms because it allows us to store state that we care about between invocation of meta calls. And that allows to implement composition and all the machinery that is required to keep up assumptions about overarching language. And then there are a lot of type classes that make it possible to go between the extension and the language. And those should be generatable itself. So let's see how the extensions are formed. So imagine you want to extend a language with the new feature functor that allows addition of literals. We write our functor assuming existence of some overarching language. We do some bookkeeping to remember the name, because the variable will be abstracted away after we close the section. We remember that our functor depends on it. We assume that there is an evaluation function for overarching language. We implement the evaluation factor for our piece of language we care about. We do bookkeeping again, and that's it. We also can automate it further by writing example section with all the assumptions to streamline the enumeration and bookkeeping about things we know about overarching language. But then we need to compose it. We need to write a fixed point on types. That's manual. We need to map the things we define with things we remembered, assumed about the language in sections. Then we run compose to compose them, and then remember again, because we might need it further in our proofs. So the things that we've done so far, we implemented pieces of Lambda.js a la carte, and they include call by value Lambda core, conditionals, unrecoverable errors, and mutable references. The thing that suggests that we are on the right track is that if one wants to write interaction between different functors of our language, it does not require to add any code to existing functors. We just write a new functor that knows about existing functors, and then write pieces we care about reduction semantics and syntax. We preserve across all these things a preservation theorem that is very weak, but it's like a sanity check. We automated section templates almost. Then there is a term specialization, because section abstract over the variables it mentions, and then we need to re-specialize it back. And instances for tight retracts that work, that define the how we jump between extension and overarching language are also automated. Things that are yet to be done, and there are a lot of them, probably more than listed here, but we interested in taking care of reactivity, of testing the approach on dialects, for example, on React. More language features are required for sure, and the key piece here is that after we are done with the Lambda JavaScript formalization, we can try to implement the feature that is actually compliant with ECMA standard without touching anything that is in another functors. Then, of course, fixed point and composition does not work yet. And the theorems that we want to have for overarching language are also to be proved. And one thing that is very further work is that actual in-language invariants about language constructions are also yet to be even approached. So thank you for listening. This is a presentation. This is a repository that changes very fast. And I want to finish with saying that JavaScript has a well-maintained standard that allows us our mechanization. Extensibility is crucial for keeping mechanizations up for a language they mechanize and to make them useful. Functors enable modularity, and metaprogramming enables composition. Thank you.
Any questions for Kirill?
By unique reduction, you mean determinism, basically, or it seems fairly strong. It's a one-step reduction should be a functional relation or something like this?
Like that, if two terms are, I think it's basically this. So if we can arrive to some expression by reducing, there is no two ways to arrive to it. So the reduction is deterministic.
How often does the language change? Like, we saw a lot of proposals to change JavaScript are adding libraries and things like that, and most of those I would imagine would not kind of add new features to the language. How often do new, like, fundamental features get added that you need to change control flow or something like that that would really have a substantial effect on the semantics?
Like Signal's proposal about reactivity is one, but the nice thing about this approach is that hopefully we are able to prove things about even non first-class objects of the language, but things that are actually used in practice. And this approach it suits for doing so. Because, for example, signals that are in reactivity proposals, they are built on top of existing features of the language. But we want to prove how they behave, even if they fundamentally do not introduce anything new to the language.
Thank you.
It's often a difficulty when you want to teach programming to people that they have to learn a language that has all the features right from the start. Do you have the impression that your solution is would provide a good support for teaching material? Because you make it possible to start with a small language and then...
Actually, yes. I never thought about it, but that could work. Yeah, because the simple core, you teach it and then you gradually extend while students watch or even extend themselves. Yeah, that would work.
Okay, any more questions? One last question? If not, let's thank Kirill again.
Thank you.